Okay, welcome back everybody. This is the third machine learning lesson that we'll be doing. Last time what we went over was quite a few chapters, so I'll just go over it in the machine learning mastery with Python outline here, which we should be finishing today. There's just a couple more chapters. But what we went over was some feature selection. So mostly PCA is what you'll probably use. Looking at evaluating the performance of machine learning algorithms with resampling. So this is typically done using k-fold cross-validation, and an extension of that special case is leave one out cross-validation, and there's a nice automated way to do that within the Python scripts. We started looking at machine learning algorithm performance metrics. So this was kind of a crash course in statistics. So looking at evaluation metrics like accuracy and receiver operating characteristic curves as well. We did some spot check classification algorithms. So we looked at a couple different classification, a couple different regression algorithms, and figured out a way that we could actually compare the performance of them together. We then went into automating machine learning workflows with pipelines. So this was really nice if you wanted to do, say, take a data set in and then do some pre-processing and then run that through some machine learning algorithm. You can do that in really nice, compact and concise ways. So we have just 4 chapters to go over today, and even a couple of these are quite short. So we'll go first into improving performance with ensembles. So you can take a bunch of different models and evaluate them together, combine them in different ways, and get improved performance by doing that. We'll go over performance algorithm tuning. So essentially what we can do here is tune some of the parameters, and from there we can hopefully get a little bit better algorithm performance. And then finally, the last step here is saving and loading your machine learning models. So here we'll train some sort of algorithm, save it to a file, and then load it back up and test it on some new data. And the last thing is kind of an outline for a predictive modeling project template. So we'll jump right into it with these performance ensembles. So there's a couple different ways that you can combine different machine learning algorithms together. So there's bagging, which is building multiple models from different subsamples of the training set. So an example of this would be like if you were to do k-fold cross-validation and you say your k value is 10, you would end up with 10 different algorithms based on different subsets of the data that you're using for the training and validation subsets. You could then take all of those models together, combine them, and use them as a collective to make a prediction on some sort of new data set. Boosting, you can build multiple models of the same type, which learns to fix the prediction errors of a prior model in the sequence of models. So I think that this is something that is really popular these days. We'll go over a brief algorithm of this, but essentially it uses the previous iterations of the machine learning to try and build a path for an optimized way forward. And then there's voting. So you can build multiple models and simple statistics to combine predictions, essentially. Let's see. So for bagging algorithms, these are mostly the trees. So bag decision trees, random forests, and extra trees. These are things that can be automated. And then the boosting algorithms, we get this ADA boost and stochastic gradient boosting. And then for the voting ensembles, this is something that's not really built into Python. So you have to spend a little bit more effort into actually programming it. We'll go into that as well. So these are different ensembles. So why don't we just dive into the code directly here. So we will look at all the trees here. So these are the bagged ones first. And as I click through these, you can see that except for the case of the voting ensemble, you end up with very similar looking code where essentially all you're doing here is changing the model that you're using. So this extra tree classifier in this case, which is just imported at the top from scikit-learn. And then there's some sort of hyperparameter, typically like the number of trees and the maximum number of features. And all these codes run in pretty much exactly the same way. So I won't spend a lot of time here, but basically you can run each of these and what it spits out is the mean result of all the different models that it's making. This one's 75%. If we go to the random forest classification, we get 76%. Extra trees. This ADA boost, 75. They're all performing very similarly to each other. And then the final one here is this voting ensemble classification. This one trains a logistic regression, it looks like, and a decision tree for the second, and a support vector machine for the third. And then it combines all three of those together into a single voting classifier. Does anybody have any question about how these work? Yeah, so it's likely that you'll get different values depending on, well, it has this random state here, but a lot of these algorithms are empirically driven and they may have a randomly initialized initial state. So, if you're starting from a different state, you may not end up in the same local minimum that the algorithm is trying to solve the error gradient towards. This voting ensemble one is kind of fun because this lets you do the shotgun approach. You can really just load as many different models as you want, try all of them, and just let it decide, what linear combination of them is going to be the best estimator. Okay. There's no more questions there. I'm going to go on to optimization. So here in chapter 16, it talks about tuning your algorithm. And for example, with a ridge classifier, essentially there's one parameter that you want to put in, which is called alpha, and it's a number that ranges from 0 to 1. And there's two ways that you can kind of do this. The first way is a random search. So you can specify a parameter grid here. And what it will do is randomly select here 100 different values of alpha to try with your classification. It'll go through all of those and then it'll figure out which one worked the best. So this is a way that is really good if you have a bunch of different values that you want to go over. So if you say, instead of just only having alpha, you have like 5 or 6 tunable parameters, which is something that comes into play when you're doing neural networks, but maybe not so much for a ridge classifier, then doing a randomized search could be what you want. So here says the best random search accuracy, 77.1%, occurs with an alpha value of 0.76. So that's the one that it randomly jumped on. Then you can also do a grid search where you explicitly define an array of values that you want to try for alpha. So the difference here is you just put parameter grid in here in the grid search CV. So that's imported up here from the scikit-learn package. And if I run this again, it gives me a different value of alpha, which is really funny. I went over this code earlier, and it turns out the value of alpha doesn't really matter that much for this classifier. So this example is not really a very good illustration of it. So I can prove this to you if I go here and reduce my grid search. So let's say I just only have 0.001, 0.0001. I run this, it'll still get the same accuracy with that value of alpha, but I promise it goes through all of them. So that's what this function does. And typically you will get different values. So that's pretty much it for grid searching and parameter tuning. Depending on the algorithm that you choose, there will be more or less parameters that you want. So here you could do, say for like a support vector machine, you have a C value and an alpha value. And those are really useful parameters to do a grid search over, for instance. Does anybody have any questions about optimization? Okay, so we will move into the last real content chapter here. So that's chapter 17, and this is saving models. So we finally made it. We made it to the point where you've gone through all the steps of choosing the model that you want to use on your new data, and you want to be able to actually do that. So the best way to do that is to spend a lot of time training your machine learning algorithm, and you want to save that state to a file so that you can load it later and then just apply that function that you've optimized to new data. So you can do this either with joblib or pickle. They both work pretty well. Joblib is supposed to be a little bit better for NumPy arrays. I'm not exactly sure why. For all my algorithms, I use pickle. I've not run into any problems with it. They only differ here by obviously how you actually import these. So from pickle and from joblib, they both have these functions called dump and load. So what you do here, say in this logistic regression, you fit this model, which is logistic regression, define a file name, and then you want to dump model into file name. So model here, basically this fit function will take the model that you've defined and will optimize the parameters within this variable, and then you dump that variable into this file. And then I can come in here into my folder, and then I have this finalized model.save. And you'll notice the file size is actually quite small, and that is really nice. Typically with machine learning, it takes a really, really long time to descend down the error gradient and find an optimal solution. But once you've found it, depending on how many tunable parameters you have, you typically end up with a fairly small file. And then when you're applying it to new data, that's typically really fast as well. So the majority of the time that you spend is usually in the training process. So depending on the learning algorithm you have and how much data you have, training can take anywhere from a couple seconds, like in these algorithms that we're trying here through this book, or weeks to months for a lot of convolutional neural networks in particular. So this is how you save the file with dump, and then you can load it by just saying load file name, and then you just call load model and you score it on these testing X and Y subsets, which were defined up here by this train test split. So you can do this here with joblib, and you can also do this with pickle. The notation for saving a file is a little bit different for pickling. This is a more typical way of opening and saving files. with Python, you have this open file name, and then this WB basically means that you write to the file and overwrite it, and then RB means that you're going to read from the file. That's really the only difference between the two, though. Does anybody have any questions? Okay, that's all the content in the book, basically. So the last chapter here, chapter 18, is a project template. So essentially all this is doing is it's giving you a template for doing your own project. And what I highly encourage is the best way to learn this is to have your own data set that you want to work on. And I know that everybody in Roman Krem's class, this is literally what your final project is going to be, is you're going to need a data set, and you're going to have to go through each of these stages in order to present what you've done. So really roughly, you basically prepare your problem, get all of your data, load it into Python. You want to summarize your data, and then prepare it for machine learning, evaluate a bunch of algorithms, do this tuning with the grid searching and stuff that I just showed you guys, and then finalize it by saving a model and applying it to new data. So that's really top to bottom how these projects work. In terms of the most time that you're going to spend, you'll probably spend a lot of time once your stuff is loaded in preparing the data. So step 3 over here, pre-processing makes a huge difference on the accuracy of machine learning. Typically, you want to do some sort of normalization. A lot of times PCA is really helpful, and a combination of those can be even more useful. And then you're going to want to explore your space of different algorithms that you can use to assess the data. Hopefully, it doesn't take too long to improve the accuracy, but that's a linear process. You only want to do things that are constructive. You're not going to want to keep any changes that give you a worse accuracy, for instance. So you're always pushing to make it better. The finalizing the model is always really easy. It's just a couple lines of code that you need there to save the file, and that's pretty much it. So there's a couple examples of this actually in the book, chapter 19, 20, and 21. These are like fully detailed project outlines, and we can actually just kind of go through one since this has been really quick here. So this iris data set here is a classifier for iris flowers. So go through this here. Essentially what we have is a data frame, which is our data set over here. So we have a total of 150 samples. And for each of these samples, we have a sepal length, width, a petal length, and a petal width as well. And then a classification. So a setosa for some of them, versicolor for other ones, and virginica. Is that how you say it? Virginica. So this will go through all the stages of figuring out which algorithm is the best to use. So first thing that this prints out here is the actual shape of the data structure. The second is this head function, which prints out the first 20 data points. The third is this describe function, which tells you the mean, standard deviation, upper and lower quartiles, max values for each of the input variables. And then for class in particular, it tells you how many samples belong to each of these class. So we have 150 of them. We have 50 setosa, 50 versicolors, and 50 virginicas. And then it also tells you the data type there. It then goes down and does some plotting. So I'll make this a little bigger. Yeah, this is more plotting of the input data here. And these are some nice histograms of the distributions of sepal lengths and petal lengths and widths. And then over here, it looks like we have those same histograms from the time before here on the diagonal. And then this is the linear correlation between each of the variables here. So we see something like petal length and petal width is highly linearly correlated, but sepal width and petal width are not necessarily linearly correlated. So this gives you an idea of maybe you don't need both petal length and petal width. You can see that the histograms here, for instance, actually look fairly similar to each other. So when you're trying to do dimensionality reduction, these are the sort of things that you want to look for. And of course, you can do this using PCA just to do some unsupervised learning on it, and that's fine. Then they go on to split a data set into training and validation subsets, and then define a bunch of different machine learning algorithms to try. For each of them, they do a k-fold cross-validation, and they all work to different degrees of success. So what it looks like here is that this here is the accuracy, I believe, as a function of the machine learning algorithm that's used. And it seems like the K neural network and the support vector machine are working better. And then over here is a confusion matrix. So normally we were working with the diabetes classifier, and that was either a 0 or a 1 for whether or not they had diabetes. But this time we have 3 different classes. So instead of a 2x2 confusion matrix, it's a 3x3. So it's still actual prediction on the x-axis and machine prediction on the y-axis. Your goal is the same. You want all of your data to be along this diagonal line here, and the ones that are in the off-diagonal elements are predictions that were gotten wrong. So then over here, the last thing that it does is it makes predictions on the new validation data set. And this is everything that's predicted here. So the confusion matrix, of course, is this. 0.9 is the accuracy on the new data. And then there's a classification report down here. So it gives you the precision, recall, F1 score, and all those things. So that's just a top-down sort of approach to a new data set. And you'll just have to fill in the blanks for whatever data set that you end up working with. So does anybody have any questions about this? Yes. Eric says almost all or some of the models are computationally exhausting. Example, the unsupervised k-means learning algorithm is dependent on the number of runs you make on your data. Definitely, that is definitely true. And he has a question here. So does run any of these models change any of the results with significant numbers of runs? Here, I believe it, what is the random seed here? It sets seed equal to 7. So I would expect these numbers to be exactly the same because they're choosing exactly the same subset of patients to use. So if I run this again, yeah, it looks like KNN is still that 0.98333. If I change the seed number here, yeah, you see it's 0.958 now. So it is dependent on the subset of patients that you use in the training and validation stages. And that's something that's good to keep in mind. It's a good comment. Thanks, Eric. Okay, if that's it, then we'll stop here.